Hi and hello. In this session, let's take a look at what is IPv6 and some of the design considerations in case you are planning to transition your enterprise networking from version 4 into version 6. You must be knowing that version 6 is very large in size with a hexadecimal notation compared to your version 4's decimal notation. And with several new features and functionalities in version 6, it's a huge transition from version 4 to version 6 in many ways. For an example, do you know that there is no broadcast in version 6? Yeah. All this obviously makes IP version 6 a complex one to understand and a very complex to implement. Especially the transition or migration from version 4 to version 6 is very complex due to the fact that there is no backward compatibility from V6 to V4 as such. I mean, you can bring few solutions to connect your V4 to V6, but the V6 protocol as such is not built to talk to version 4 directly without solutions like NATing and things like that. I believe this is a good topic to discuss and bring some clarity on what should you know about version 6 and necessary considerations during your design phase. In the enterprise networking, it is still majorly IP version 4 in use, and version 6 is still not popular even in large enterprise customers. Sooner or later, V4 will not be sufficient for all the IT requirements, even in the private space, which is within a company's internal network itself. Or when the internet facing requirements are growing like anything in the current IT trend, existing IPv4 public networks cannot address these needs. Hence, enterprises, whether small or large, they eventually start transitioning towards IPv6 addressing. Let me just cover the basics of IPv6 before I get into the design considerations. We'll try to compare the V6 with V4 as much as possible so that it will be easier for you to understand. This is how IPv6 address is represented. This is documented in the RFC 4291. I'll give you the link in the description. You can refer them. IPv6 addresses are 128 bits long, wherein our IPv4 is just 32 bits. In version 4, we used decimal notation, but here in V6, we use hexadecimal based characters to represent the address space and separated with colons instead of dots. Just like 4 groups of 8 bits in version 4, V6 addresses are represented as 8 groups of 4 hex characters. Each group consists of 16 bits, and the unofficial name for that is hextet, like octet in version 4. Each 4-bit, which is a hex, can be called as a nibble. Let's look at few examples, different ways of IPv6 address representation, and how do we compress the fields to make it easier. We'll take a look at that. So in this, the first address is the formal representation of 32 nibbles grouped together as an IPv6 address. Look at the second example, which is basically a global IPv6 address. And in that, the third and fourth hextet, you don't have to show all zeros or all 4 zeros, or you don't have to show all 16 bits as hex in there. It is okay, and it is a right way of representing with a single zero, which means you can omit all the leading zeros. And the same case in the sixth hextet, the leading zero is omitted, but the trailing zeros should be mentioned. So this is another right way of representation. We'll see few more examples here with the right way of representation. So it is important to understand that what is the right way to compress or simplify the IPv6 notation. In the first example here, third and fourth hextet has consecutive zeros. So anywhere you see a consecutive zero, which is 16 bits of zeros consecutively in an IPv6 address, they can be compressed into double colons. So you don't have to show them separate zeros in an IPv6 field. You can replace that with double colons, and that basically represents consecutive zeros between the other fields. Look at the second example here. It's a multicast address. So there are 6 consecutive zeros within the IP address, and that can be replaced as double colons. That makes FF01 double colon 101 as the right way of representing instead of this. And the third, the loopback address, instead of putting all 7 hex states with the zeros and then 1, you can just represent that as double colon 1. And the fourth example, instead of all zeros to represent an unspecified address, you can simply show that as double colon. So these are the ways IP address can be represented, or the right ways to simplify the IPv6 address. There are different address families in version 6, just like what we see in version 4. Version 4 will have multicast, unicast, and broadcast address classes. Similar to that, we have multicast, unicast, and anycast in version 6. We don't have a broadcast address type within version 6. Yes, IP version 6 extensively makes use of multicast. For example, if you remember the ARP feature, which uses the broadcast in version 4. So we don't have an ARP in IP version 6. Instead of ARP, we have something called Neighbor Discovery Protocol, NDP, that basically works using multicasting. Okay, getting back to the address types or address families. So within unicast, we have again different types of addressing, which is linked local address. This is somewhat similar to the 169.254 range in version 4. Basically, this address used local to a link. It is non-routable. Linked local addresses are basically designed to be used for addressing on a single link for purposes such as automatic address configuration, neighbor discovery, or when no routers are present. These are the use cases. The linked local address usually begins with FE. And then you have unique local, like this is like a private IP address range in version 4, and the private IPs in version 4, what we know as RFC 1918, like 10.0/8 networks, the 172.16 or 192.168 series of networks. It is similar to that in version 6, where it begins with FC and FD. So basically these addresses can be used within one single administrative domain or within a private network. These cannot be routed towards internet. This is very similar to that of the IPv4 private IP address use cases. And then we have a global IP address. This is again like a public IP address in IP version 4. This is routable across the internet, and currently there is a /3 reserved for this public IP range. It begins with 2 and 3. Then you have a multicast range which begins with FF. These are the address families within IPv6 you should know of. So a few more information on this. So you can only advertise /48 into the internet in IPv6. You cannot advertise smaller than this prefix length in the internet if this is going to be a provider independent address range. And from the protocols perspective, where you have ICMP and DSCP for version 4, similar to that, you have ICMP version 6 and DSCP version 6 for IP version 6. So just like I said before, instead of ARP, you have Neighbor Discovery Protocol, NDP, and within that, the ARP request, instead of using a broadcast, it will use multicast for the neighbor solicitation. So I hope these basics are enough to get into the IPv6 design considerations and planning. Here you can see the current state of IPv4 public pool. This is the current data from the RIRs. Almost all the public IP version 4 addresses are exhausted. This will be one of the key rationales behind why organizations should start migrating towards IP version 6. Assuming as an organization you're already running your entire IT with IP version 4 and you would like to transition towards v6, or certain part of the application or network you would like to start using version 6 for any reasons and advantages, how do you approach this requirement? As we discussed in our previous session, before you create any design, any architecture, you need to first understand the requirements and constraints clearly. So the first step would be to assess the readiness of the current environment. That will give you the constraints which the infrastructure is going to present to you. First, check your network devices, firewalls, and other security services, especially applications and servers like that. You need to check their hardware and software, whether they are compatible to run IP version 6, whether the tools used in your environment will support IP version 6. Any external services like internet, WAN, cloud sort of connectivities, will they provide you the version 6 connectivity? Whether the third-party connectivity and services, would they offer you such IPv6 services? So after doing this exercise, after you get all the answers, so you will basically learn the gaps and compatibility issues from the assessment, and you need to use this data to plan the transition further. Depending on the current readiness of the environment, it might involve additional cost and a lot of planning and coordination from all the teams like network, security, server team, the application team, the desktop teams. It takes a lot of planning and coordination for a successful rollout of version 6. So what would be the steps to follow? Look at in terms of efforts needed to design and implement. You may need to procure additional hardware or software, and consider that cost as well in case you have unsupported assets. And the timelines to complete all this to be planned. Basically, you need a project plan. You need a project manager to track this plan. Very importantly, impact to the BAU during this transition from V6 to V4. That needs to be assessed. The risks need to be clearly called out and documented. This will basically involve identifying the scalability, capacity of existing hardware, and the performance impact which may be caused during the transition. So all these exercises need to be done after the readiness assessment. Let's go back to the first step we discussed before, which is the designing of IPv6 architecture. Since we are considering a brownfield scenario here, we need to have a plan to roll out version 6 as seamlessly as possible without breaking the existing production environment. Using dual stack is considered to be a good design choice, since we will not break the version 4 connectivity, and in parallel we get the option to build version 6 infrastructure. When the infrastructure is end-to-end IPv6 ready, then we can remove the version 4 seamlessly, which is almost seamlessly, though it's not that simple. Let's look at how that can be done. In case you're not aware, a dual stack means every IP addressable interface will be configured with both version 4 and version 6 addresses. So start with enabling version 6 in the network core infrastructure and move towards the access layer. Then enable version 6 in your WAN, internet edges in a sequential way. Hopefully all the providers are supporting the version 6 now. Then move on to upgrading the other infrastructure components. This could be servers or storage or any other components. Finally, enable the application for IPv6. So in my experience, this will be the hardest part, where most of the legacy applications will not support version 6 as such. And this needs a lot of work and will have an impact in the BAU. Once these tasks are successfully done and tested end-to-end in version 6, then we are pretty sure that we don't need version 4 in the environment. Then we finally remove the version 4, and that concludes the version 6 rollout project. This absolute V6 environment may not be possible in current IT environments, especially in the brownfield scenarios. Having so many dependencies external to the organization, and not everyone will offer you V6 services. So let's say that there is an IPv4 island within the organization that's not supporting the upgrade, like an unsupported application or a hardware which doesn't support version 6 or a dual stack options. So these scenarios where you will have an IPv4 islands within your own environment, and you'll have to have some sort of bridging between these two islands, the version 4 and version 6. So there are choices, there are design choices where you can bring in NAT solutions to connect these two version 6 and version 4 world together. So it is called a 6.4 NAT. So any 64 NAT capable device which will be connected to both version 6 and version 4 networks via different interfaces can translate the addresses between version 6 and version 4. So this is similar to the way v4 NATing happens. So we can run this sort of workaround design for a period of time till we roll out IPv6 entirely. So just so you are aware, it's not like dual stack is the best choice for rolling out version 6. So you need to be cautious of version 4 to version 6 coexistence issues and implications in the devices. For an example, when your routers are enabled with both v4 and v6, they are basically doing double work. For v4 they do arc cache, for v6 they do neighbor discovery cache. For v4 you have a table and v6 you'll have another routing table. So running separate control plane functions basically for both protocol versions. So your existing hardware and OS should be scalable to run this way for a period of time till you remove version 4 entirely from your infrastructure. So we covered the transition plan in high level and looked at some of the design considerations while rolling out version 6. Let's take a deep dive into the version 6 address planning. We looked at few addressing types before, like link local, unique local, and global addressing. Which address type will best fit for the endpoints, the network, or in the perimeter? Should we create a design similar to the way we used to do in version 4, like using the private IP space, the 10.x series or 172 series within the internal network, and use the public network range towards the internet? So you will end up using NAT solutions in the perimeter to translate from your private network into public network. Do we want to do the same thing in version 6? So there are several recommendations on this particular design scenario. Mind you, there is no clear winner or just one design choice here. Your design decision should consider all other possibilities as well. So in general, the recommendation is to use global IPv6 address range directly in the internal network. So be it the network infra or servers or application, and advertise the same in the internet as well. So hence no need of any complex address translation solutions in between. So it makes the design simple, just one address space everywhere, no breaking of connection in terms of NATing or any translations. So another misconception is that NAT is considered as a security solution in version 4, but it is not the case. NATing is introduced in version 4 purely to conserve IP addresses due to the limitations in the version 4 public IP schemas. So we don't want to bring in the same problem into the version 6 world. Version 6 we have the largest public pool, so there is no such IP address conservation need to be done here. Hence we can directly make use of the public IP pool within the LAN, and we can choose to advertise them in the internet as well. So let's say you need to secure your internal network from the external world. Yes, firewalling is one of the ways you can restrict the access towards your internal network. And you can also choose to advertise only the prefix which needs inbound internet access. So the rest of the public v6 prefixes, you don't have to advertise them into the internet. So that is another way of securing your LAN network. So now we made a decision on what IP space to use, and we procure that global IP range from an internet RIR or ISP. Let's say we get a /32 range. The next step is to create a global addressing plan. The addressing plan should consider globally, and don't start the addressing local to a specific locations. So identify the structure of the addressing plan in a top-down approach, unlike in version 4 we used to do it the bottom-up, which means we calculate the number of hosts needed per subnet and we identify the number of subnets needed for a location. And so this is how we used to plan the version 4. But in version 6, you do it in the top-down way. You have plenty of addresses. It's a huge address space, so you don't have to be conservative in version 6. So always consider reserves. Don't worry about the number of hosts. Always assign /64s for any endpoints based network. In a version 4 world, you would have considered a /24 by default to assign to any VLANs or any the endpoint, the host subnet. In version 6, just don't count the host. You just assign a /64. So that's the best practice. And have a hierarchy in the addressing plan when you create it globally. So that means a few bits reserved for indicating the country, and a few bits reserved to indicate the region, and then few bits to represent the location, and then the building, then the purpose, function of that particular network, like that. So when you create a IP plan this way, so by looking at an IP address, it will be easier for everyone to understand. So the IP address will give more meaning. By looking at it, people can identify an address belongs to which region and which location and which campus it belongs to. So that can be easily done. Let's take an example that you take a /32 and try to create a global addressing plan. Just allocate the first 4 bits for the country, for representing the country, then the next 4 bits to represent the city, and then the next 4 bits to represent location and building and something like that. So this gives you a proper hierarchy in the IP addressing schema, right? So allocating 4 bits basically gives you 16 combinations there. So you can have offices in 16 countries. Within each country, you can have 16. You can have offices in 16 cities, and within that you can have 16 locations or 16 buildings or something like that. This is just an example to create a IP planning. And let's take that, finally you have a /48 when it comes to a specific building or a specific office, something like that. This means that you will get 2 power 16 combinations of /64 subnets, assuming that I'm going to use a /64 for all my endpoint subnets, that I can still get 65,000 subnets of them. So I think this is very generous. So based on this example, this is how we create a global IP plan. Now you would have realized how difficult it is to create addressing plan and using them. It is recommended to always use some sort of IPAM tool, and certainly not using Excels in the way we managed IP version 4, and use DHCP services and not leaving it to manual or automated IP addressing. So there are a few other recommendations in the network design with IPv6. So though we discussed about using a /64 wherever possible, it's not the case everywhere, right? So let's say you have a requirement to create a loopback address, or you have a requirement to create a point-to-point link address. So how do you choose? How do you subnet them? In IP version 4, we used to create a subnet depending on the number of hosts needed within it, right? If I just need 2 hosts in a point-to-point link, we go with a /30 or a /31. We are used to this. If we need a loopback address, which is just one address, so we used to create a /32 there. So are we going to follow the similar conservative approach in version 6? So there are RFCs which detail them clearly. So the simple answer is no, don't do that. Don't be conservative in V6. You have plenty of addresses available. So the RFC 6164 states that you can use /127 in P2P links, like the way you use /31s in version 4. But allocate a /64 dedicated for the point-to-point link. So which means when you create a plan, you allocate all /64s for every use case, including point-to-point links with a /64s. But while configuring it, you use a /127 for the point-to-point links. And then it comes to the loopback addresses, you can use /128s, but again still allocate a /64 for this purpose. But while configuration, you use a /128s. And then for the subnet allocation for the host, that for the endpoints subnets, use only /64s. So even you need just 100 IPs within that subnet, do not divide that /64 further into smaller prefixes. So use /64 consistently all across your network infrastructure with /64s for the endpoint requirements. So this is clearly defined, documented in the RFC 7421. So I guess this is it. We discussed what is IPv6. We tried to understand the IPv6 complexities. We tried comparing them with the IP version 4's the way of working. And we tried to understand some of the design considerations when you try to transition your network into version 6. We looked at the complexities. We discussed the best practices to be followed when you create IP planning. We basically looked at the sequence of how you transition your network into version 6. And so that concludes the IPv6 design session. Thank you for listening and good luck.